Welcome to this physics revision video, specifically adapted to the 2022 Advance Info for the exams provided by AQA. We're going to be mainly focusing on the triple science higher course. So physics is a separate science, it's also called. But if you're combined science or doing that course but foundation, then there's still going to be a lot of useful stuff. We're going to go and have a look at the advanced information. Please subscribe if you find this helpful. So for triple science higher, we are covering all of this plus energy resources and nuclear radiation, which haven't been announced that they're not going to be assessed, but all of the other stuff is not going to be assessed for you, so you don't need to worry about any of this. And we're also covering the two required practicals here. So for triple science foundation, it's a similar thing, apart from you will need to go and find some stuff on the electric circuits, because unlike for higher, that has not been taken out of your exam. You will be assessed on that, so you might need to go to Seneca or BBC Bitesize for that. And there's also a bit on background radiation, I think, that could possibly be assessed. So for combined science higher, we're covering energy changes, energy transfers, the particle model. We are not going to be covering pressure, so you might need to go and find something for that, as well as atoms and isotopes, although that is all common content with chemistry. That's like the history, as well as how atoms work. We covered that in chemistry, so you should be familiar with that. And then you guys have two required practicals that aren't going to be featured in this video, so you can skip the density required practical and the insulation required practical, because you need the specific heat capacity required practical, and the electric circuits required practical for current and voltage. And you might also need to go and look at something about fission and fusion, because that hasn't been taken out for you either. And finally, combined science foundation, we're covering this. We're not covering electric circuits. You need to look up, go and find some resources on current, potential difference in resistance. They're going to be very important for you. We are covering these two though. You may also need to look at background radiation, fission and fusion a bit, because that hasn't been taken out for you. And your required practicals are the same as combined science higher, so you will need to go and look up specific heat capacity and electric circuit diagrams as well. But that should be it, all of the content in this video, apart from static electricity actually, which isn't coming up in combined science higher, or foundation, but I mentioned that. But that should be it. Let's crack on. One of the main topics in physics paper 1 is energy. It's very important to know how energy is stored in objects, how it's transferred, because they're going to ask you about that. So if you want, pause the video, have a go at these 27. That's how you're going to revise and get this knowledge into your head most effectively. But now we're going to go through what you need to know. So a system is essentially just, in physics, a system is the object or the group of objects that we're focusing on and we're talking about. So if we're talking about energy being transferred between two objects, those two objects would be our system. A closed system is a system where nothing leaves or enters. So it's like all the energy and matter you have is kind of fixed in that system. There's a fixed amount, a certain amount. There's 8 ways energy can be stored, and you need to know them all. We're going to go through some in more detail, but you need to kind of have an understanding of how they work. So kinetic energy, that's just like the energy an object has when it's moving. Thermal energy is actually, as we're going to look at later, very similar to kinetic energy. It's the heat of the particles when they move, but that's kind of kinetic energy. We're going to go through this a bit later. Chemical energy is just the energy stored in the bonds of a substance. Again, we looked at this in chemistry. Shouldn't be very important in physics, but you might be asked, I don't know. Magnetic energy is just the energy in a magnetic field, essentially. There's electrostatic energy, and that's kind of electric energy, but it's not moving, because electricity is more of a form of energy transfer. That's how energy is being moved. But we come and look at static electricity. If you're doing physics as a separate science, we come on and look at that later. But electrostatic energy, it's just like the energy between like opposite and alike charges, so how opposites attract, alikes repel. That's that kind of energy. There's also nuclear energy, which is just the energy in the nucleus of an atom, and it's released by fission and fusion, but both of those processes have been kind of taken out of most people's exams, so we don't really have to look at those. And then there's potential energy, so gravitational potential energy. It's like saying that due to gravity, this object has the potential to have energy, because if we let go of an object, then obviously it's going to fall, and it's got the potential to have energy, essentially. Same with elastic potential energy. If we pull back a rubber band, for example, it has potential energy, because if we let go, that energy, it has kinetic energy. So we kind of describe that energy of pulling that is stored in it when it's pulled back, elastic potential energy. So there are also ways energy can be transferred between the different stores. The first one is through heating. So as we're going to look at later, that's essentially just how the particles move and pass on that movement, therefore passing on energy through conduction and convection, which we're going to look at later. There's work done. Work done is essentially just a way of saying that energy is being transferred. You can have mechanical work done, and that's where a force does work and transfers energy. So, for example, if I throw a ball, my arm is transferring energy to that ball, but I'm doing work because I'm applying mechanical force to that ball through my hand. There's also electrical work done, so that's as charges move through a circuit and they encounter resistance, they do work and therefore transfer energy to overcome that resistance, and that's essentially how electricity is like that. That's just a way that energy is transferred. And then obviously there's like waves and radiation, so like light waves, that's a way of that energy is being transferred. So you need to be happy with describing how energy is transferred between different stores, because they're going to ask you that. So there's this one, the energy transferred when a person throws a ball upwards. You need to consider how the energy is transferred, whether it's work done mechanically, electrically, by heating, by waves and radiation, and which store it's going from and which store it's going to. That's why these questions are usually 3-mark answers. This one has quite a few processes. So the energy, it comes from our arm, doesn't it? Because our arm is putting kinetic energy into the ball, causing it to move upwards. That energy in our arm, in our body, is chemical energy, because it's generated by the chemical reaction of respiration. So we're converting chemical energy by doing work into kinetic energy to throw the ball upwards, and as the ball goes upwards it slows down. And where's that energy going? Because it's not just disappearing, because energy doesn't just disappear. Well, some of it, as the ball does work against the air resistance, does mechanical work, it's going to be transferred thermally into the surrounding. It's going to dissipate, essentially transfer thermally into the surroundings. That's generally, when we talk about energy dissipation, it's usually into thermal energy, as that's kind of how the particles vibrate individually. But also, we're in a gravitational field, which means that the ball just can't travel upwards forever. The kinetic energy is being transferred into gravitational potential energy, and when that ball stops, all the kinetic energy is now stored as gravitational potential energy, but that ball is going to start falling, and that's the gravitational potential energy being turned back into kinetic energy. And then when that ball hits the ground, if it's a particularly bouncy ball, the energy is going to be transferred into elastic potential energy, as the ball is going to squish down and then spring up again, and that whole process of kinetic energy to gravitational potential energy back to kinetic energy is going to happen again. Obviously, as the ball falls as well, there's some work being done against the air resistance, which causes some energy to dissipate, but a lot of energy as well will be lost. As the ball hits the ground, it transfers energy into the ground. Energy dissipates out through the ground, mostly as thermal energy. Again, talk about energy dissipation, you generally think thermal energy. So here's another simple one more simple one to have a go at. The energy transferred when a car slows down. So where's the energy starting as? The energy's starting in the kinetic energy store, isn't it? Because the car's moving and we're slowing it down, we're reducing the car's kinetic energy. How are we doing that? Well, we're putting brake pads against the wheels, and this causes a frictional force, which causes more work to be done by the wheel, which transfers the kinetic energy stores in the wheel into thermal energy stores, because as mechanical work is done, the energy dissipates out and transfers thermally. So the energy transfers when a kettle boils. So there's that work being done, that electrical work being done through the component, which is the kettle. So we say that energy is being transferred electrically to the thermal energy store of the kettle, and that thermal energy heats the water in the kettle, so it transfers from the heating element, for example, to the water. That's an energy transfer by heating. Remember, that's one of our energy transfers, isn't it? And as the water gets hotter, the energy in its thermal energy store is increased, and that causes it to boil. As the particles get faster, it's got more energy in its thermal energy store. So the key when describing energy transfers is simply to describe the energy store that the energy is starting in, the energy transfer that's happening, and the energy store that the energy is finishing in. And maybe if you can see that friction or air resistance is causing mechanical work to be done, you might want to mention that energy is dissipated if the question is for a lot of marks. So usually you'd have to remember a ton of equations, but now that you get your physics equations sheet, I'd go and get that now. If you want to reference all these equations that we're going to be talking about, you don't need to remember them, but you do need to remember the units, because obviously they're not going to give you everything in the right units. You might need to convert units. So what are the units for the kinetic energy equation? So the kinetic energy equation, half times mass times velocity squared. Energy we measure in joules, J. Mass, generally we measure it in kilograms, kg. And velocity, we're going to measure that in meters per second squared, because obviously speed is distance divided by time, meters divided by seconds. No, sorry, I only said squared because we're having velocity squared, so we're going to have to square it. So gravitational potential energy, we have the mass in kilograms, we have height in meters, and then gravitational field strength, that's always going to be 9.8, because unless they have a question about something on the moon where there's a different gravitational field, but the gravitational field strength on Earth is 9.8, and the units for that are newtons per kilogram. And finally, elastic potential energy, similar to kinetic energy, half times the spring constant times the extension squared. Again, you get given this equation, so you only need to know how to put the figures in. So the spring constant is measured in newtons per meter, and the extension is obviously the amount the spring is out. That's measured in meters, and once again, energy is in joules. We can't use the equation for elastic potential energy when the spring has exceeded its limit of proportionality. We look at this more in paper 2, because the extension and the force applied to the spring are directly proportional up to a certain point. We call that the limit of proportionality, but yeah, again, we look at this more. Now, specific heat capacity, it's the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So each substance has a different specific heat capacity because each substance has a different arrangement of atoms, and therefore the way it heats up and the rate at which it heats up is going to be slightly different. The specific heat capacity practical is only featuring in the combined science exams, but the units for the equation to calculate the change in thermal energy, you'd be using the specific heat capacity. You get given the equation. So we have thermal energy in joules, mass in kilograms, specific heat capacity. This is a difficult one. We measure specific heat capacity in joules per kilogram degrees Celsius. So just remember always to work in joules, kilograms, and degrees Celsius. If you get given something in grams, 99% of the time you're going to want to convert it to kilograms. So power features quite a bit in the Physics Paper 1 exam. It's essentially the rate at which energy is transferred, or the rate at which work is done, because obviously referring back to our energy transfers, work done is energy transferred essentially, and that's why the equation is energy transferred over time. Obviously you get given that, and we measure power in watts and time in seconds. That's very important. So if you get given minutes or hours, you've got to times by 60, convert it back down to seconds, and obviously work done is also in joules, same as energy transferred. Energy is always in joules, remember. So you could be asked for an example to illustrate this definition of power. So for example, if you have two motors that lift the same weight. So I don't know, let's take two diggers. Two diggers lifting at the same weight of a substance. One will do it fast. The one with more power will do it faster, because if you both time them to see how far they can lift it in, say, 30 seconds, if the one with the higher power will be transferring more energy, because power is the rate at which energy is transferred. So the more energy that's transferred, the higher the digger will be able to lift the substance. So the conservation of energy principle states basically the energy cannot be created or destroyed. It can be transferred usefully, it can be stored, or it can be dissipated, and we mean just spread out into the surrounding area, so essentially transferred but in a less useful way. That's what we mean when energy is dissipated. It's just stored in a less useful way. We often describe it as being wasted, usually because it goes into thermal energy. So if we have, for example, a lamp, we want 100% of its energy to go into creating that light, but some of it will be dissipated as heat energy into the environment. And note quickly, if we remember, light is not an energy store, light is an energy transfer, because it's a form of wave and radiation, as is sound. Sound is a way of energy transfer. That's important to remember, because it comes under our kind of waves and radiation method of energy transfer. So energy is transferred in closed systems. There's never a net change in energy. The total amount of energy in that system never changes if it's a closed system, because nothing can no energy can be created or destroyed. That's the basic rule of energy. And if it's a closed system, we know that no energy can leave the system or enter the system. So that means that the total amount of energy cannot change. So frictional forces and air resistance, as we've covered over here, we said that they cause mechanical work to be done and therefore energy to be dissipated. So obviously in industry we want to reduce this as much as possible. So if you think about friction, it's kind of like no surface is ever going to be smooth. So if you have two quite bumpy surfaces on an atomic level, then they're going to catch over each other and kind of make it harder to slide your way along. So we can reduce this energy dissipation by using a lubricant. So like an oil maybe, or a liquid. This just reduces the friction, because it just allows the objects to flow easily and slide easily over the top of each other. So energy is transferred by heat due to conduction and convection, and it can be by radiation, but it's usually by conduction and convection. Now would probably be a good time to address the difference between kinetic energy and thermal energy, because we'd refer to when energy is transferred by heat, it increases the temperature and therefore the thermal energy of the objects. But on a molecular level, when we look at the individual moving particles, we say the individual particles have kinetic energy, while the actual object that all of the particles are in has a thermal energy, and that heat. And again, we're going to look on temperature being the average kinetic energy in a bit. But conduction is what happens in solids when you have those a moving particle. It happens especially in metals, which is why we say they are good conductors. Again, there's two types of conductivity: thermal conductivity, how easily an object passes on heat. That's through conduction by when the particles vibrate. It knocks against other particles, causes them to vibrate, gain kinetic energy. And as this kinetic energy spreads throughout all the particles, they all gain kinetic energy. That increases the thermal energy store of the object. So that's thermal conductivity. Also electrical conductivity, which we look at in chemistry more, where how easily it's just whether particles can transfer electricity or not due to the charged ions or electrons, but that's chemistry, not physics. Convection then happens in gases and liquids, where you heat the molecules. It's different from conduction because liquids and gases can flow. So if you heat a gas molecule, it's going to rise up. And as it rises up, I'm sure you'll have covered this in some other subject. As it rises up, then it's going to cool and therefore sink back down. and then it's going to get heated by the heat source and rise back up again, and it kind of creates this circular convection current, we call it. And it's also important to remember that down by the heat source, where lots of particles are sinking and not moving as fast, it's going to be denser because the particles are close together, but up where the particles are just beginning to cool but they're moving very fast because they've moved up, it's going to be less dense because the particles are moving faster, so they're further away from each other. So we reduce the dissipation of energy from heat simply by using insulation. So we use lubricants for frictional forces, and we use insulation due to heat. This could be like loft insulation in your loft, or it could be like wrapping newspaper around your cup, or having a particularly polystyrene cup to keep your coffee warm. For example, those are all forms of insulation. Again, insulative objects that have a low thermal conductivity, we say. As I've talked about, you don't need to know a specific definition for thermal conductivity, but as I talked about, if an object is thermally conductive, it passes heat on very easily. So if it's an insulator, then it doesn't pass heat along easily at all through conduction, and therefore maintains a constant temperature for a longer time. Metals are the materials that have high thermal conductivity, and ionic compounds because their particles are packed tightly close together in the lattice formation, so when they vibrate, the other particles are very close together. Non-metals are different because of the way they're bonded. They pass heat on less easily, and therefore we call them insulators. So, for example, we have our polystyrene, that's an insulator. So how can we optimize the walls of a building to reduce the energy dissipation through heat? Well, apart from trying to make the temperature on the outside and inside as similar as possible so that heat doesn't transfer as much, well, we can make walls with a low thermal conductivity so that they don't cause heat to dissipate out of the room very quickly. We can make them thicker so that the heat takes a longer time to dissipate out. We can also install cavity walls which have a gap, but it's like two walls with a gap, or for example double glazing in windows. There's a gap between the glass, and this means that heat dissipation through conduction is kind of stopped because obviously there's an air gap. It has to then convection happens, but it happens slowly, and it just causes less heat to be dissipated. We can also put insulation in that cavity to reduce heat transfer even more. So again, summary: low thermal conductivity, thick walls. Maybe we want a cavity wall to disrupt the energy dissipation through conduction. So now we have the insulation practical appearing obviously in the physics as a single science paper, but not the combined science paper. It's quite an easy one, which is quite nice. All you're going to do, you're going to have a container with different insulating materials that you want to test out. Maybe some newspaper, maybe some polystyrene, maybe some tin foil if you want to investigate how good an insulator tin is. Probably not very. So you're going to boil some water, maybe in a kettle. You're going to pour it in, take the initial temperature. You're going to then wrap your container that you've just poured the water in the material that you're testing out. So maybe wrap it in newspaper, put polystyrene layer in. A key control variable here is the thickness of the material. You can do a separate experiment, see how the thickness of your material affects its insulation. But for this, investigating different materials, you want to keep the thickness the same. So you may need 10 layers of newspaper to account for one layer of polystyrene if your polystyrene is particularly thick. And then after 5 minutes, you're going to open it all back up. You're going to take the temperature, note down the temperature change, pour the water away, and then you have to make sure that your container is at room temperature before you repeat the experiment. That's another important variable, the temperature of the container, control variable. And the temperature of the outside as well is another control variable, so you want to keep all the other temperatures the same. Hopefully the start temperature of the water is going to be very close to boiling, but by taking temperature change we can account for the 1 or 2 degree differences by taking the temperature at the beginning and not just assuming it's 100 degrees, because obviously in the time that you've poured the water from the kettle into the container, it's going to have lost energy. And then when you've finished, the material that has caused the least temperature change is the best insulator. And we've been through some of the control variables. And the final thing for this topic, the energy efficiency. Obviously you have that equation now on your physics equations sheet, so you don't need to worry about it. So we measure efficiency as a percentage, and the energy we measure in joules. You might get given powers, it's fine. You can do useful power over total power, just as you do useful energy transferred over total energy transferred. Power obviously is in watts, while energy is in joules. And they might give you an energy transfer, ask you how to make it more efficient. I think that's higher tier only, correct me if I'm wrong. But again, that's just using the things that we've discussed up here. So if you're having problems with frictional forces, you might need to use a lubricant. Air resistance is a frictional force, but obviously lubricants don't work on gases. So you could make your material or substance more aerodynamic to reduce air resistance, or if you're having trouble with heat transfer by heat, use an insulator. Obviously different scenarios will require different kinds of insulation, but that's just kind of common sense. So now we're going to have a look at energy resources. I really like this topic because it's really focused around current problems with climate change. We obviously need to find alternatives to fossil fuels. Essentially, we're just going to be evaluating all our different renewable sources and renewable options, why they're good, why we're not using them on a large scale, because there are a lot of problems and teething issues with our renewable energy sources. So a renewable energy resource is essentially one that is replenished as we use it. So for example, wind power, as we use wind, more wind is there to be used. We never use our wind up fully, whereas non-renewable fossil fuels, the coal in the ground, eventually all the coal is going to run out. Even though coal does get replenished, it gets replenished over millions of years at a far faster rate than we're using it up. So our two non-renewable energy sources, fossil fuels and also nuclear power, is not renewable because it's from uranium or plutonium in the ground. Our three main fossil fuels you need to know about: coal, oil and gas. In terms of CO2 emissions, coal is the worst, oil is the second worst, natural gas is the best, emits the least CO2 out of the three. So there's 7 renewable energy sources that you need to know about. There's biofuels, there's the free water ones, so there's hydroelectric power from dams, there's tidal power, there's water power, there's geothermal power plants. We can harvest the heat from volcanoes, for example, in Iceland. There's solar power from the sun, because that's light energy, isn't it? That's all the energy that we can use solar panels to harvest that energy. And the final 7th one, wind. As I talked about wind turbines, we can harvest that kinetic energy of the wind as energy. So what do we use our energy resources for? Well, electricity generation, heating homes, as well as transport. So which energy resources are we able to use for transport? So we cannot put a nuclear reactor in a car. That is not going to work. This is why we use fossil fuels, because they're reliable. We can just burn them in the car and generate energy, whereas things like wind-powered cars, tides, water waves, a lot of the renewable ones simply aren't going to work. We can use biofuels, and we have been using biofuels. And by biofuels, I simply mean that's burning plants or waste plants, and they're considered renewable because as you burn them, you can grow more. But having said we can't use any of the other ones, we can actually, because as we're developing electric cars, we can start to outsource the electricity from a power plant or any one of these renewable sources. So heating our homes, generally at the moment, once again, we're reliant on the fossil fuels just because of how reliable they are. We can use gas and oil in our homes to heat water, which we can put into radiators and heat our homes, keep them warm. But once again, we can burn biofuels instead if we want to be more renewable, and also carbon neutral, because obviously as we burn plants we're emitting CO2, but as we're growing more plants they're taking in the CO2 that's been emitted, so they are considered carbon neutral, even if it's a bit sketchy in practice. In Iceland, as I mentioned, where we have lots of volcanoes and underground heat, we can use the geothermal energy through a heat pump to heat our homes, so that's an option. And then obviously there's the electric heaters you can buy, and they can be supplied from our mains supply, which is fed off nuclear power. It could be fed off any one of these renewables, or it could be fed off fossil fuels as well. So, considering energy resources, they're not, for a lot of the exams, they aren't a major focus, but if you could still be asked to evaluate the pros and cons of one of these. So what you want to do is you want to think about the reliability. You want to think about the environmental impact, maybe the availability, but also importantly the economic cost of creating the power plant, of running them. So let's start with fossil fuels. Most widely used because they're most reliable. And this just means that we can burn them on demand to produce electricity on demand, whereas, for example, the sun isn't always out, so we can't always use solar power. We can't rely on that 24/7. But fossil fuels we can, so that's why they're considered the most reliable. Economic cost of fossil fuels is quite interesting because they are fairly cheap to extract and run, even though the power plants themselves might cost a lot. You know, you have those big turbines to turn the generators, but you don't need to know about that stuff until paper 2. Nuclear power is just as reliable because it's generating energy all the time, because the fission reaction is going on 100% of the time. Environmentally, they do not emit any carbon, apart from in the construction of the actual power plant, of course, but the fission does not emit carbon or any greenhouse gases for that matter. However, the nuclear waste generated by uranium power plants is an issue. It's dangerous. We can't dispose of it. Economically, well, the nuclear power, the nuclear fuel, is quite cheap to kind of source and get. The actual nuclear power plant, and decommissioning it and burying all the nuclear waste, that is quite an expensive process, which makes nuclear power not the cheapest option on this list. And biofuels, quite reliable because obviously it's a fuel, we can burn it when we want to, produce energy when we want to. They're carbon neutral, supposedly, because obviously we can replace the plants, grow them back at the same rate as we harvest them. Economically, it's quite expensive to refine the plant into the biofuel, because it's not just like burning a log on a fire. We turn plants into like actual fuels, and that process is quite expensive. There are other environmental costs because the land, it uses a lot of land to grow them over. We could be using that for food. We may have to clear forests to grow biofuels. It's all destroying ecosystems, killing species that relied on the space that we're now using to produce biofuels. So maybe, they're not the wonder fuel that we thought they were when we first discovered that we could use them. So in terms of reliability, wind is quite unreliable, because even though we're the windiest country in Europe, the wind is not blowing all the time, so we cannot generate electricity from wind turbines all of the time. Environmentally, they don't emit any CO2 apart from in the manufacturing of the actual wind turbines themselves, but they do have some disadvantages. Birds that fly into them tend to be killed. That's a problem. They also take up a lot of land. On land, we have to destroy the environment around them to install them, because we have to bring over loads of big machinery to actually put them up. They spoil the view. They're visually intrusive. And while the cost of making the wind turbine is quite high, actually running it barely costs anything. Oh, and the noise, of course. Wind turbines are actually quite noisy when you're close up, causing further disruption to the local ecosystem where you're putting them. So hydroelectric power, it's reliable unless, of course, there's a drought. So if you're in a particularly hot country, they might not be so reliable. Economically, the dams cost quite a lot, but again, the costs to running them, it's not actually that bad. The environmental impact, while it doesn't emit any CO2, when it's actually running, again, we've flooded a huge amount of land, destroyed a huge amount of ecosystem, and all that rotting vegetation that we've flooded is actually going to emit greenhouse gases anyway. So maybe hydroelectric power, dams are not actually as green as we thought. Geothermal energy, reliability, it's very reliable. as it's kind of always hot in those areas. Availability this time, because obviously it's it's only in volcanic areas. It also does very little damage to the environment. No CO2 because the heat is already there. We don't need to burn anything to generate the heat energy. However, it's fairly expensive to build the power plant, and obviously the other con, as I mentioned, is the availability. Geothermal energy can only be used in a select handful of locations. Tidal energy is fairly reliable because we know that there are going to be 2 tides per day due to how the tides cycle around. However, some tides are bigger than others, so maybe not 100% reliable. So what the tidal energy, to harness it, we have to build like a dam across an estuary, and this is going to harm the local ecosystem there. It's going to prevent boats from being able to travel up the river. It's going to cause problems for tourism because they're not going to like the view disruption. And once again, the economic cost of building one is high, but the economic cost of running it is low. Solar panels, again, that's similar to a lot of renewable energy. It's unreliable because the sun isn't always out. From an environmental perspective, it doesn't emit any CO2, although the energy used to manufacture it, and it's quite polluting to dispose of. All of the harmful chemicals in there, they can be quite polluting. And once again, the cost of manufacturing is high, and the cost of running is minimal, very low. And finally, harnessing the power of waves in the ocean. You're putting little turbines underwater by the coast. Environmentally, that's quite good because while the initial costs, once again, they're quite high, you don't have to pay anything to run them. Environmentally, they don't cause pollution, they don't cause greenhouse gases to be emitted, but once again, they harm the view. They harm the ecosystem, and boats. It's quite risky when the boats are travelling through them. They could go over them and damage the boat, they cause damage. Okay, so over the course of the 20th century, our electricity usage increased massively as our population grew. We used it for more electrical appliances, we developed them. However, in the 21st century so far, our electricity usage has actually been shrinking a bit as we've made our appliances more efficient. Our trends in different energy resources, then obviously much of the 20th century, it's been almost entirely fossil fuels, but now, as we've become more aware of climate change, there's a push towards renewable energy resources. And there's also on the specification, you need to know, scientists cannot solve the problem alone of renewable energy because it comes down to politics and what politicians decide to implement as an energy strategy for their country. So, for example, a really expensive energy generation method is not going to be popular, and therefore politicians won't want to do it because the cost to taxpayers is going to be higher, and that's going to make the politician less popular. Location as well. Nobody wants a massive power plant built and destroying their lovely view and their local walks or whatever. People argue, not in my backyard. They don't want it near them. Even if they agree with it, nobody wants to be staring into a wind turbine or trying to sleep while the wind turbine is going crazy outside, making lots of noise. And reliability as well. Politics is generally going to drift towards fossil fuels because they're reliable. If we try and supply our entire national grid with wind power, what happens when the wind drops? Does everyone just have to live without electricity for a day? We're developing batteries to store energy when the wind has dropped, but that technology is nowhere near ready. It's not there yet. If you're doing physics as a separate science and you're on the higher paper, you get to skip out all of the stuff on electric circuits and all of that complicated stuff about voltage and current and series and parallel circuits. None of that's going to come up, which is very, very nice, let me tell you. But we do have a bit on how energy is transferred electrically, linking back again to the thing we did at the start about energy transfers, but specific to in electrical circuits. Then we look at the national grid, and static electricity is a topic that is only appearing in the physics as a separate science exam papers. So pause the video and have a go at these 13 or 20, depending on which paper you're doing or not. So the power transfer is directly related to potential difference in current and resistance. There's an equation that goes along with that. You don't have to remember it. You will have power is voltage times current. Power is the current squared times the resistance, because voltage is current times resistance. You have that equation, but again, you don't need to learn it. Remember that the units for power is watts, potential difference is voltage, volts, current is in amps, and resistance is in ohms. You need to know those. So the power transfer of a circuit is linked to these three because the higher the potential difference, the higher the energy of the circuit has, which means that more energy can be transferred round the circuit, essentially. The higher the current, now current is essentially the rate of flow of charge, so the higher the current, the more rapidly the charge is flowing around the circuit, and therefore the quicker energy is transferred. And obviously power, we're referring as energy, the amount of energy that's transferred over a period of time, the rate of energy transfer. And resistance, the more resistance in a circuit, the more work that has to be done electrically, because that's how energy is transferred in circuits. And therefore, if more energy is transferred over the same amount of time, that is a higher power transfer. There's two equations that we're going to be given to calculate the energy transferred by electrical appliances. Obviously, it's linking into that P is power is energy transferred divided by time equation, because energy, you can rearrange energy transferred as power times time. Energy transferred, there's another equation, is charge flow measured in coulombs, C, that's very important, times the potential difference in volts. Those are two equations, so depending on which what kind of data you're given in the exam, you can choose which one. That's the key to using the physics equations sheet. You must check which data you've been given fits the equation correctly. You may have to use multiple equations, especially at the back of the paper. They'll probably give you a question asking you to do that. So when we're describing electrical energy transfers, because it's quite complicated how energy is stored and transferred electrically, so we can either say that energy has come through the mains, as it will do with a toaster, because you plug it into the mains, or from batteries, but we'll get into batteries in a minute. So in a toaster, the electricity, it comes from the mains supply from your national grid, which again we're about to look at, into the thermal energy store of the heating element of the toaster, because obviously you've got to describe how work is done electrically due to the components in a circuit have a resistance which causes energy to be transferred into those components. That's what you need to know and write in every single question that you get about electrical energy transfers. That's very important. So once energy is into the heating element of the toaster, you're going to get heat transferred through infrared heat rays, infrared radiation to the toast, essentially. So you have two energy transfers, electrical work done, and then radiation. Batteries store energy chemically, as we discussed in chemistry, because the chemical reactions cause potential difference to form. It converts chemical energy and transfers it electrically into the fan, and at the motor there's resistance, obviously, which causes more work to be done electrically, which causes energy to be transferred. Because where you get energy transferred, there's a drop in potential difference, and a drop in potential difference causes energy to be transferred. There's an explicit link between the two. So as that electrical energy is transferred through the electrical work being done at the motor uses that energy as kinetic energy, which causes the fan to spin due to the kinetic energy of the motor. So yeah, we've just been over this. So the chemical energy is transferred electrically through the circuit, because the flow of electricity is actually kind of complicated. It's, scientists are still debating over it, so it's not a GCSE topic really. You have that drop in potential difference as work is being done electrically, causing energy transfer at the component, whether that be the heating element or the motor, or it's most likely to either be a motor or a heating element. I can't think of an appliance that will use the energy in a different way, but you might get one. Just describe the specific component that is being used. So yeah, in any electrical energy transfer, you have to describe how work is being done electrically, causing energy to be transferred. Charge flow is measured in coulombs, as we discussed. So the power rating of an appliance is simply the maximum amount of energy that can be transferred per second, essentially, because that's power, isn't it? Energy transferred over time, rate of energy transfer, and it's the maximum amount that can be safely transferred. So the higher the power rating, the more energy that's transferred in a given amount of time, and therefore the faster work is done, because work done is energy transferred, as we've discussed. However, there are downsides to a high power rating, because the more power put in, that doesn't mean more energy is being transferred to the useful energy store that we want. It could be that extra energy is just going into being wasted, dissipating as thermal energy. And also lower power ratings, they cost less to run because you're using less electricity up in a given amount of time. So the national grid is a system of cables and transformers spanning the entirety of the UK, and it connects power stations where we generate electricity to the consumers, individual homes, businesses and industry where electricity is used. So the national grid needs to transfer enough energy to supply the entirety of the UK, and this means that it needs to transfer a huge amount of energy, which means that it has to have a really, really high power because of that direct link between power and energy transferred. And again, then we can look at our formulas. To get a high power, we need either a very high voltage or a very high current. The problem with a high current is it causes loads of energy to be transferred and dissipated as thermal energy into the environment, and this is why the current in the national grid is as low as possible, and therefore we have a really, really high voltage, which means that we can transfer as much energy as possible, making it as efficient as possible. So transformers, we look at them more in paper 2, but basically it's an iron core, and each side you have wires twisted round, and due to the electric field created, the electricity is transferred between the wires. But if you have more wire that's twisted more, so if you have more turns on the wire, the second wire that the current actually, the electricity actually goes into, then this increases the potential difference as the electricity jumps the gap and goes into the secondary coil. And that's how we increase the potential difference, make it really, really high. We make it 400,000 volts when it's traveling in the cables that we see overhead. But that's obviously going to kill a human if we ever come into contact with it, so we need to use step-down transformers to make it safe. So the mains voltage is only 230 volts, and to step it down, we put more turns in the primary coil of wire in a step-down transformer so that the potential difference decreases at the consumer. And it's worth noting that because transformers are almost 100% efficient because of their energy transfer between the coils, the power of the secondary coil is the same as the power of the primary coil, and therefore you can get the equation that potential difference times current of one coil is equal to the potential difference times current of the other coil. And that's the relationship between the power of the primary and secondary coils of the transformer. The national grid is efficient, again, because we use a high potential difference and a low current, but also because the power stations, they run well below their maximum power output. This means that there's energy that we can, extra energy that we can put into the national grid at times of high demand in the evening where everyone's at home watching TV. Maybe there's a major football match on that everyone in the nation is watching at the same time. We can put more power into the national grid, and by operating at less power, we're making it more efficient. So static electricity builds up when two objects are rubbed together, and due to the friction of those two objects, sometimes the negatively charged electrons from one of the objects, they can rub off and become attached to the other object, causing one of the objects to have lost electrons and become positively charged, and the other object will have gained electrons and become negatively charged. Which way the electrons go, it depends on the materials, but the materials are always insulators, because in insulators there's electricity cannot flow because they aren't conductive, they don't have free electrons or ions to move. And this is where the electrostatic energy store comes from, because the electric charges cannot move. And it's also important to remember that it's the negatively charged electrons that are transferred, not the positive charges, because the positive charges are the protons, so they're inside the atoms, they don't move, they stay inside the nuclei of the atoms. Charged objects interact with each other, while like charges repel each other, so two positives repel each other. These are electrostatic forces and electrostatic energy, and opposite charges attract and pull towards each other, they attract each other. So, electric fields are created around any electrically charged object. So it could be a wire that's carrying a current, it could be something that's charged with static electricity, but an electric field, it just kind of shows the forces that are caused due to the charged object. So electricity always travels from positive to negative, so this means for an isolated positive charge, all the electric field lines are going to be travelling away from the charge, and for a negative charge, all the field lines are going to be shown pointing towards it. Sorry, I drew that incorrectly, so you should have the arrows pointing towards it. The closer the lines are together, the stronger the force is. So you see closer to the charge, the stronger the force is. So as these two get closer, their forces of attraction become stronger because the lines are closer. And as you can see, as we get further out, the distance between the lines increases, and therefore the strength of the electrostatic force of attraction or repulsion will decrease. So this is just building on what we covered back up here in static electricity. Very obvious. If a charged particle is placed in an electric field, it's going to feel a force. If the charges are alike, they're going to repulse each other. If their charges are different, they're going to attract each other. And obviously the distance between the two charged particles causes the strength of the electric field to decrease, and therefore the attraction or repulsion force to decrease as well. So sparking, if you get a continuous build-up of static electricity, maybe on a hot day, something has become really charged so that its potential difference between it and the Earth at 0 volts is very, very high, sparking can occur. And this is because this high potential difference causes this electric field around it to become very, very strong. And it only really works if the charged surface is close to the Earth or an earthed conductor. And that's just a conductor that connects to Earth to allow a pathway down to Earth. And so when you have this really, really strong electric field, it causes the electrons in the air to be removed, ionizing the air effectively, and therefore when the air is ionized, it becomes conductive. It allows a current to flow through the air, so a current can flow between the conductor and either the Earth or the earthed conductor, and this is like a spark as an object kind of, or as the charge, I should say, it leaps the gap between the charged object and the Earth, because it doesn't want to be charged. And as it kind of leaps this gap, it causes a spark as the current flows through the air as a spark. This is usually very small. Lightning is a great example of this. The electric fields of the neutrally charged ground and the charged clouds and the high potential difference between them, causing air to be ionized, current to flow through it as a massive spark, aka lightning. We're going to move on to have a look at the particle model of matter and how particles and energy and matter interact. So we've got this bit on like density and changes of state, and then this bit on how energy and matter interact. This bit is not going to be in the Combined Science Higher exam, so if you're doing Combined Science Higher, you can skip these 11 questions, but otherwise pause the video and have a go at these. So density essentially measures the amount of matter in a given volume of a substance. That's how we get the equation that's going to be given to you on your equations sheet. Density is mass divided by volume. It's kind of like a amount of mass in a given volume, if you will, and its units. It's very important to remember the units because they don't appear on the physics equation sheet. Kilograms per meter cubed. So here is the actual particle model of matter for a solid and liquid and gas. We have the solid here, obviously because of the strong bonds in place. They're bonded together well, the particles are all held together in fixed positions. In liquids, enough of the bonds have kind of broken so that it can flow. The particles aren't held together in their fixed positions, and in gases, all the bonds are broken and the particles are all separate, flying about individually. And you may remember in chemistry we talked about solids having the least energy and gases having the most energy, because as you add energy, it gives more kinetic energy to the particles so they can move, vibrate more, and as they move and vibrate more, more of the bonds start to weaken and break between them, and that causes a change in state from solid to liquid to gas. But that's kind of more chemistry, but again it's linked to energy, so it's linked to physics. And then we also have, in terms of density, solids are the densest, because as you can see in the given volume, we have the most amount of particles. They're closest together. There's the least amount of gaps. Gases are the least dense because there's the least amount of particles in the given volume. There's huge gaps between the particles, which means they're less dense. So questions 4 and 5 are about the density required practical, which isn't coming up in combined science. So the density of a regular solid object is definitely the easiest one. You can measure its mass using a balance, and then you can measure its volume. Because it's regular, you can measure the volume really easily, unlike the irregular solid. You simply say it's a cube. You can measure a side and apply your basic shape formulas. So just square the side length of a cube to find its volume. If it's a rectangle, obviously you do length times width times height. If it's a sphere, or any other kind of shape, you should hopefully be given the formula to work out volume. But irregular solids are trickier. You have to describe them. You have to have a eureka can. Go look it up if you don't know what it is. It's kind of that can with the spout near the top. So what you do is you fill that eureka can full of water right up to the spout, so that any mass that you add into that can, water is going to overflow, go through the spout. You need to get and put a measuring cylinder underneath the spout so that you can catch all the water that gets displaced from the can. Remember, displaced is a very important word here. And then you take your irregular solid and you put it in the eureka can gently, to ensure that no water splashes out and you get an accurate reading. And then as the water's going to, excess water that's been displaced is going to drain out of the spout into the measuring cylinder, and you're going to get the volume of water that's equivalent to the volume of your irregular solid in that measuring cylinder. Once again, the mass you can weigh using a balance. There's a handy conversion. 1 milliliter is equivalent to 1 centimeter cubed. You can also measure density in grams per centimeter cubed. So it's very important to keep an eye on the units that they're asking you to give it in. Make sure you're happy converting between meters cubed, centimeters cubed, kilograms and grams. Obviously that's a maths topic, so I'm not going to go into that. And then when you have mass and volume, you just put them into the formula to calculate density. So for liquids, it's going to be slightly different because obviously because the particles aren't fixed, their mass and therefore density could be slightly uneven. So what you have to do is you have to take an average density. So let's say I've got a litre of a liquid and I'm trying to find its density. What I'm going to do is I'm going to place a measuring cylinder on a balance, and I'm going to put 100 mils. So you want to take like it in gradual parts. So here I've split the litre into 10. Obviously if you have something smaller, you'll split it into smaller bits, but you don't want to split it too small, otherwise you'll be there forever. So I'm going to put 100 mils into the measuring cylinder. I'm going to record the volume. I'm going to record the mass. Remember that for volume, 1 milliliter is equal to 1 centimeter cubed. That's a very important conversion you need to learn for this practical. And then I'm going to repeat that for every 100 milliliters. And then because I've got the mass and volume for each of the 100 milliliters, I'll draw a table, put mass, volume, and then density, because then you can calculate the density of each 100 milliliters. Then you can take the average by finding the mean. You should know how to do that. And then your average density will give you your most reliable value for the density of the liquid. So we talked about physical changes and chemical changes a tiny bit in chemistry. What a physical change is means that we don't end up with a new substance, because in chemical changes, the chemicals go through chemical reactions, we turn reactants into products, we get new substances. A change of state, we don't get a new substance, because water and ice are exactly the same substance. One just has more energy and its particles are in one's particles are in fixed positions. They're just in different forms, and if you kind of reverse that change in state, so if you melt and then freeze ice, then you're going to get exactly the same ice back again. So it's physical change, not chemical change. Another important thing, there is no change in mass when a state change occurs, because you still have exactly the same number of particles, as long as it's a closed system, of course. Just remember that. Because if you change the state into a gas and your gas goes out into the environment, then that's not really a closed system. You are going to end up with a change in mass, but we kind of covered this in chemistry a bit, didn't we? And sublimation, you need to know that that is the change of state from a solid straight to a gas. You don't need to know the process, you just need to know that sublimation is from solid to gas. So, when we talk about the internal energy of the system, we're talking about the energy stored by the particles. So, the definition is it's the total energy that the particles of a system store in their kinetic and potential energy stores. Remember, those two energy stores are very key to the definition of internal energy. And this kind of links into both kinetic and thermal energy, and what we mean by temperature and heat. Temperature is essentially a measurement of the average kinetic energy of the particles, because the difference between kinetic and thermal energy, individual particles, because they are moving, they have energy, they have kinetic energy, whereas the object or the system that those particles in, we say, have thermal energy. Because, if we heat a spoon, it doesn't start moving from side to side visibly, does it? So we can't say that the actual system has kinetic energy, the actual system has thermal energy, but the particles in the system have kinetic energy. So thermal describes the object's energy, but kinetic energy is kind of the particle's energy. Obviously, if it's a car and it's moving, then the actual object has kinetic energy, but if it's not moving, only the particles are moving, then we say the object has thermal energy and the particles have kinetic energy. So this links to what heat and heating are, because they are energy transfers, aren't they? Because if we heat a substance, we are adding energy to the substance through motion of the particles. Therefore, like transferring energy to the particles of the system, and this increases the internal energy, because the internal energy is the total energy that the particles have in their kinetic and potential energy stores. So that includes their kinetic energy stores when they're moving around, and this heat transfer leads to an increase in temperature, aka the average kinetic energy of the object, which can also lead to a change in state if the temperature increase is high enough. So let's say the temperature of a system increases, the average kinetic energy of the particles increases. The size of that temperature change depends on a few different factors, and this links back to our specific heat capacity equation. If you think back to our change in thermal energy is the mass multiplied by the specific heat capacity multiplied by the temperature. So the mass could affect the size of the temperature change, because obviously the particles vibrate and the energy will spread out throughout the system. Each of the particles makes up its mass. The more particles, the more mass, and the more energy you need to raise all of the particles' kinetic energy by a certain amount. Obviously, also, therefore, the amount of energy we put in affects the size of the temperature change, because if you don't put in much energy, you're not going to get much faster particles, and therefore you're not going to get a much higher temperature change. But the other thing is the material of the system, because each material has a different layout of particles and therefore a different specific heat capacity, because if we remember, specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. So it's almost a measure of how conductive a substance is to heat, and how easily heat and kinetic energy can be transferred through the substance. Because if you have a high specific heat capacity, then you're going to need lots of energy to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. So you'd predict metals that have a low thermal conductivity to have a low specific heat capacity. So latent heat is another type of heat that you need to know about. It's essentially referring to the energy needed to change the state of a substance. So specific heat capacity, we're talking about changing the temperature, the average kinetic energy. Latent heat, we're talking about the energy needed for a change in state. So let's say when we melt ice, we put in energy, so the temperature, or boiling water might be easier to visualize actually. We're putting in energy to the particles, so the temperature is increasing, the average kinetic energy of the particles is increasing, they're getting faster. We know from chemistry that means their bonds are weakening. But when we come to the boiling point, the temperature stops increasing. And this is because we're still adding energy and therefore increasing the internal energy of the particles, but the energy is not going into the kinetic energy store of the particles, it's going into breaking the actual bonds between the particles. So what we get is this kind of graph, if you will, where we have temperature on the y-axis, time on the x-axis. As time goes on and we heat the substance, transfer energy to it, the temperature, the average kinetic energy increases. But when we reach the melting point, the temperature stops increasing, even though we're still applying heat, as the energy goes into breaking the bonds. So we get flat spots at the melting and boiling point. And this point here is just where we've stopped heating, and we've started decreasing the heat and making our system cooler. So we reach the condensing point, the same thing happens. We get a flat spots where the temperature does not increase or decrease at the melting and boiling points. The majority of the nuclear radiation topic has actually been taken out of the Triple Science Higher Exam, but there are some bits that haven't been mentioned as not coming up at all, so you will be assessed on some of this, and this is really the essence of nuclear radiation. We've got alpha, beta, gamma particles, we've got count rates, we've got half-lives, and we've got contamination. So pause the video and have a go at these 20. So, radioactive decay is all to do with isotopes. Now, if you remember back from chemistry, isotopes are atoms of the same element with different numbers of neutrons. Atoms can have many different numbers of neutrons, and only if some of those atoms are known as stable. The other ones that are unstable, because they have too many or too few neutrons, they decay into other elements by giving out radiation or lone neutrons, and they decay into other elements to become more stable, and this process is known as radioactive decay. The activity is essentially the rate at which a source of nuclear radiation decays. So we measure it in becquerels, I think that's how you pronounce it. It's in BQ, and 1 becquerel is like saying 1 decay, so 1 particle is being emitted per second. Now, be careful, because the count rate is similar but different. The count rate is basically like the frequency, so it's the number of particles that are emitted each second. So you may have heard of using a Geiger-Müller tube, and that's what we use those to measure the count rate, because they detect the radioactive particles that have been released. That ionizing radiation, they detect that and give you the count rate, which is the number of radiation particles passing through it. So that could be alpha or beta radiation, for example. And those are two of types of nuclear radiation, alpha and beta particles. Alpha particles being 2 protons, 2 neutrons, so essentially a helium nucleus. Beta being 1 electron. And then there's gamma rays, which are actually just sources, they're just energy, electromagnetic waves. And then it could also be a lone neutron as the neutron travels past, but we don't really look at the neutron. We mainly look at alpha particles, beta particles, and gamma rays. So I talked about what these two are. This is just an electromagnetic wave, which we'll look at more in paper 2. So they have symbols. I don't think you'll need to know them. Alpha is like a little special A, beta is like a special B, and gamma is like a special Y. So I don't think you'll need to remember them, but you do need to remember the properties of these particles, which materials can each of the above penetrate. And also, what are their what are their ionizing powers? Ionizing power, of course, referring to how easily the ionizing radiation can knock electrons off atoms and creating positive ions and ionizing them. That's how radiation does damage to our body, which we're going to come on into in a minute. But let's take alpha first. So alpha particles are the most ionizing, so they're the most dangerous. However, they can only travel a few centimeters in air, and they cannot penetrate anything thicker than a sheet of paper. So outside of our body, alpha particles are unlikely to get past our skin. So beta particles or beta particles, they have a moderate ionizing power, so they're kind of in the middle. They can penetrate a few meters into air, so they can travel quite far but not too far, but once again they're stopped relatively quickly through solids because they're denser. So maybe just a sheet of tin foil or aluminium foil is gonna stop it, just like maybe half a centimeter thick. It can't travel further than that. And gamma rays, as we discussed, they are electromagnetic waves, so they aren't particles, and therefore they can travel much further than the particles can. They can travel long distances. They can come from us to us from distant stars. They can travel very far. They can travel through most materials, but if you have a thick block of lead, or that is going to stop it, so it can't travel indefinitely through solids. It's the least ionizing because it's a wave. It tends to travel through rather than collide with the particles and ionize them, but it is still weakly ionizing. So now we move on to decay equations. They're actually quite easier than chemical equations, I think. So here, for example, we have radon-219 being decayed by alpha decay, forming polonium. Write the nuclear equation to show the radioactive decay. Now we write the mass number and atomic number. If you remember from chemistry, the atomic number is the number of protons, the mass number is the number of protons plus the number of neutrons. So as you can see, the number of neutrons is higher than the number of protons, so we have an unstable isotope of radon. You will be told in the question the number of protons of radon. You're not expected to know that, but you should be able to figure out the product. So we have alpha decay, and as I talked about, that is where the atom releases 2 protons and 2 neutrons. As I talked about, basically a helium nucleus. I've written the chemical symbol. If you don't know the chemical symbols, because you don't get a periodic table in the physics exam, then you can just write out the element in full. If you do, then I think you can just write it like that. You should know He is helium. So what is the mass and atomic number of helium? If we've got 2 protons and 2 neutrons, then the atomic number is going to be 2 because we have 2 protons, and then 2 protons plus 2 neutrons is 4 because the mass number of protons plus neutrons. And if we're taking this away, if we've taken 2 neutrons away from 86, then we're going to find out that polonium has 84 protons, and we're going to find out that this isotope of polonium, we're taking 4 particles away from the 219 to get 215. So that is how you do decay equations. They're not that complicated at all. You should be told these values, and you should just be able to do some simple subtraction to work out these values. So here we're going to write a beta decay equation for carbon-14 decaying into nitrogen. Now beta decay is slightly harder, but not really that much harder, because in beta decay what you have is you have a neutron decays and forms a proton and an electron, and the electron is spat out of the nucleus because only protons and neutrons allowed there, no electrons allowed. So that's what happens. That what is happening is the nucleus is essentially gaining a proton because that neutron's turning into a proton and releasing an electron, isn't it? Neutron. So if we're gaining a proton, then the atomic number is going to increase by 1, and the mass number, because neutron is included in the mass number and proton is included in the mass number, there is no change because electrons don't have any mass, do we? So there is no change to the mass number in beta decay equations, and we write this as -1 because our proton number has actually gone up 1 because we have 7 plus -1 is 6. That's kind of mathsy because we've had an increase in the mass number because the neutron's turned into a proton, so we have 1 extra proton, and that's represented through the -1 that we write by the electron. If it's easier to remember, you can think about this as like the charge, because electrons are negatively charged, so it's going to have a charge of -1, and the charge here is going to have increased by 1 because you have an extra positive charge, aka proton, here. And finally, we don't write nuclear equations for gamma decay because gamma rays are energy in the form of electromagnetic waves. No particles are being removed, so there's no change to the mass number or the atomic number. The element, in fact, stays the same element. The half-life of a radioactive isotope is simply the time taken for the number of radioactive nuclei in the isotope to halve. So essentially, each radioactive nuclei is an isotope of an element, but all those nuclei packed together we refer to as an isotope overall. So we can predict the half-life of different isotopes of different elements, basically by predicting its activity, therefore the rate at which it decays, but we cannot predict which individual isotopes are going to decay, which individual radioactive atoms are going to decay. We can't say, okay, that atom is going to decay. The process of when each atom decays is totally random, but when we have them all together, we can predict the rate at which they are going to decay overall. So we can draw a graph to show the decay, so the activity obviously being the rate. So when the activity has halved, then we know that half of the radioactive nuclei in the isotope have decayed, and therefore its half-life. So halfway down here is going to be 1 half-life, and you can actually calculate the half-life therefore by going down and finding the time on the x-axis, because this would be the half-life here. So I think question 3 was how much of the isotope is decayed after 4 half-lives. Well, where is it going to be after 2 half-lives? If this is 1 half-life, then another half-life is going to be halfway between that half-life and no activity, so it's going to be there. And what we can see is this is actually a quarter. So we've halved the half-life and turned it into a quarter. So after 2 half-lives, 3/4 has decayed. So we can do 3 here and find that that's 12.5, and then 4 is going to be 6.25 because we've kind of halved it and halved it and halved it to get to our 4th half-life. So 6.25% is yet to. We're at 6.25% of our overall activity, and therefore 93.75% has decayed. So contamination is where the radioactive atoms themselves can get on something, an object that we don't want them to get on. We say that it can be contaminated, and this is a hazard because those radioactive atoms, they can decay, release ionizing radiation, and obviously for humans that can cause us harm. As we're ionized, that can cause cancer. So irradiation is where we're exposed to radiation, essentially. So if we're contaminated by radioactive atoms and then those atoms start to decay, we're exposed to irradiation, or we could say we're being irradiated. So radiation damages the body, as I mentioned. It ionizes the atoms in our body, and that can lead to cancer due to ionization. So how severe radioactive contamination and the resulting irradiation that we are exposed to the radiation that we are exposed to, the process of irradiation, depends on which type of radiation we're dealing with, whether alpha particles, beta particles, or gamma rays, beta particles, or gamma rays. If radioactive atoms get inside our body and decay into alpha particles, the alpha particles are the most dangerous inside the body because they can cause lots of damage in a localized area, because although they can't travel far, they are the most ionizing, they have the highest ionizing power, and therefore they can cause the most damage to our cells. Beta particles, slightly less damage, but over a slightly wider area. And gamma rays are the least dangerous because they can mainly travel out of our body, and maybe only a tiny bit of ionization will happen because they have a very low ionizing power. Outside of the body, however, it's the other way around, because alpha radiation cannot travel through our skin because it can't penetrate very far at all. Beta particles, however, are very dangerous to us outside of the body because they can actually penetrate through our skin and cause damage, and gamma rays can often travel right through us and cause damage potentially anywhere, even though they have a lower ionizing power. The higher ionizing power of the alpha particles won't be experienced because they can't penetrate into our body from the outside. So when we're working with radiation, we need to reduce the risk of being radioactively contaminated, and that's why we have hazmats, protective suits. Orange, you see them in the movies a lot. They prevent us from breathing in particles, stop those alpha particles from getting inside our body and causing loads and loads of damage. We can also wear gloves if we ever have to handle radioactive substances, and also tongs just to keep them as far away from our body as possible, just in case. Because obviously the early researchers who experimented with radioactive and this kind of nuclear radiation, they were harmed and suffered. And yeah, you wouldn't want to be an early scientist working on nuclear radiation when you didn't understand what it did to you. And that's why peer review is so important, because studies that show how nuclear radiation affects our bodies need to be peer reviewed so that other scientists can check that they're valid and reliable, and it's reliable data, so that we know exactly what this radiation is doing to our body, how it causes cancer, etc. And this can improve how we use nuclear radiation in our everyday lives, and also improve how we protect ourselves from radiation, therefore keeping us safer. So here we are at the end. If you're Triple Science Higher and you've watched all the way through, you will have seen every single little thing that could possibly come up in your exam on Thursday. To revise this and make sure you understand it all, go back through all these questions again. If you were doing them while the video was playing, make sure you go back through the ones you got wrong tomorrow, because that's how you're going to really make sure you've got the knowledge embedded in your brain for next week. And obviously practicing exam questions is also a good way. Just make sure they're on these topics and not on different topics. So yeah, make sure, like, maybe practice some nuclear decay equations, or definitely practice doing some describing energy transfers, because I think you're only going to get better at those through practicing exam questions. So here are the questions on energy efficiency, and energy dissipation. We have the questions on energy resources. Make sure to answer the first four while the box is over these, because these are essentially the answers. But then obviously you can look at them to answer question 7, because you need them for that. And then we have our electrical energy transfers, which can get quite complicated, but I don't think you should have to worry about them too much, because really it's just explaining how work is done electrically, which I explained in the video. And then obviously the national grid and the static electricity bit, not for combined science, this bit. And the particle model of matter, particles and density in changing states, and then energy in matter, which has been taken out of the combined science higher exam. And then finally this bit on nuclear radiation, which should be easy. This is probably the easiest bit, because it's just learning a lot of facts. You can learn half-lives really easily, and this isn't even a major focus. This has just been told it's not coming up, if you get what I mean. It's not going to be a major focus for Triple Science Higher, this bit. So I hope this was helpful, and you should now have all the knowledge you need to smash physics, and yeah, good luck with it. I'm sure it will be nice and easy.